I'm also Westbrook, and this is Lab 6. So the purpose of this lab is to compare a computational model of a bar magnet falling down an aluminum foil tube to a physical experiment. And to make this comparison, the following equations and scientific principles are used. So we got Faraday's law, Newton's third law, and magnetic dipoles. So this is going to be our force from our magnetic field. Up here is the flux, d flux over d time. The dipole moment of the magnet, and this is how we get our current, and then this is Newton's third law over here. And on the computational model, the time for the magnet to travel all the way through the tube is 1.75 seconds. In the physical lab, the average time for a magnet to travel down the tube is 1.31 seconds. And although these are different, this might be due to experimental errors from improper measurements or errors in finding the correct magnetic dipole in Lab 4. So this is our observed experiment. This is the aluminum foil tube. And the system's the bar magnet. The surroundings is the aluminum foil tube. Our initial conditions is that the bar magnet is placed at the origin at the top of the foil tube. So the magnet length is 0.025 meters, the radius is 0.0065 meters, the tube length is 0.465 meters, the radius is 0.015 meters, and the dipole moment is 3.26 amps meters squared, and I calculated that back in Lab 4. And the assumptions is that only forces are due to electric force and gravity. And after 5 trials, the average time to fall was 1.31 seconds, and this is a slower pace than falling in free space. So here's our computational model. These are the initial conditions with the length and the mass. And then this is the function for the dipole moment of the bar magnet. And then this is the equation I got from the topical videos for the change in flux over time. I made that into this function here. And then this is for finding the force on the magnet by rearranging this equation and adding all these elements. It adds up to our net force. And then this is Newton's third law right here. And then as you can see, the velocity starts big and then kind of flattens out until it reaches the end of the tube. So possible error, this could have come from poor measurement practices. My group forgot to measure the width of the foil and just measured the total diameter. So I had to guess for the inner radius. Also, errors from Lab 4 could have given me an incorrect dipole moment from the magnet. Interpreting the simulation, so the red is counterclockwise because of the right-hand rule. The magnetic field from the current points in the opposite direction of the magnet, so the blue would be clockwise. And when the magnet is flipped, the magnet would fall faster because the south end is going down. And the experiment went about 0.4 seconds faster than the computational model. To make the model better, more precise measurements and verifying that the dipole moment is accurate would improve it. And the shape of the graph shows that it takes a little bit of time for the magnet to reach a constant velocity. It's probably due to it kind of getting more into the middle of the tube so that more of the tubes act on it. So what if the resistivity of the conductor were reduced as close as possible to 0? So if this happened, the tube would have a much greater electric force. So the magnet would be slowed at a much more magnitude. And what if holes or slots were cut into the tube? So if holes were cut, the induced currents could not form circular rings because the circuit would be broken, and this would cause different current patterns to form. And that's all. Thank you.